英語の発表を始めます。So, today I will be presenting this paper by the title of SRSA, which is Skill Retrieval and Adaptation for Robotic Assembly Tasks. So here are the information about the paper. So the paper was published in this year's International Conference on Learning Adaptations, and a TLDR is the paper proposes a framework that is able to fine-tune robot skills by predicting and also retrieving the most transferable policy from a pre-existing skill library. So a brief introduction on this paper is that humans excel at solving new tasks with very few demonstrations and also trial and error interactions. And being able to achieve very efficient data learning is also crucial for deploying robots in diverse real-world environments. And currently, the state of the art is to develop foundation models and also general policy that can span across multiple tasks. However, despite these efforts, solving new tasks in context-rich environments, for example, like robotic assembly, is still very challenging, also remains underexplored. And so this paper focuses on tackling robotic assembly. And in particular, in their previous work, they proposed to be able to learn specialist policies in a simulated environment, particularly using robotic simulators. And they created a data set of 100 assembly tasks called Automate. But a limitation of this previous work is that they focus primarily on learning a single task policy, and they start from scratch without ever leveraging any prior experience or knowledge from other related tasks. So the question for this work is that how can we solve a new assembly task by using previous policies and previous skills that we already learned from previous assembly tasks? So in one case is by doing a retrieval-based policy learning, where many studies have tried to explore techniques where to utilize data sets from other tasks for pre-training, such as visual pre-training or maybe multitask imitation learning. But previous work in robotic manipulation primarily studied more on general pick and place manipulation tasks and focus more on data retrieval, while in this paper, they focus on how we can do policy retrieval and also use a transfer success predictor. And the next part is by leveraging embedding learning for both task and skill. And in task embedding learning, usually people try to leverage shared knowledge across tasks, and they usually try to leverage maybe visual 2D or 3D images. And in skill embedding learning, on the other hand, they try to leverage unstructured prior experiences and repurpose them to be able to solve other downstream tasks. In this work, instead of trying to solve multiple downstream tasks, we try to select a single relevant skill for a new task and also try to integrate multiple embedding learning approaches instead of only one modality. So as a summary of the contribution, this paper introduces three main methods. One is a skill retrieval method, and the next, after retrieving a skill, we do a skill adaptation method, and the next, we implement the framework in a continual learning setting. And by doing this three-step framework, SRSA is able to tackle new assembly tasks by only using a skill library, a pre-existing skill library. And as a problem setup, as we already mentioned, the target is to solve a new target task by leveraging pre-existing skills from a skill library. And in this paper, the framework proposes that we first retrieve a skill or a policy for the most relevant prior task, which is the skill retrieval step. And then we can try to adapt the target task by fine-tuning the retrieved skill using skill adaptation. And the paper focuses on base assembly tasks in both simulation and also deployed in real world. So the first step is in this framework is the skill retrieval. And to be able to efficiently and also effectively retrieve the skill from a prior task and then adapt it to a new task, we need a method to be able to estimate the potential of applying a source policy to a new task T. So the intuition from this paper is that by applying the same policy to two tasks, which is the source task from the prior source task and also new target task, if a similar success rate is found, then that may imply that there's a similarity in both the dynamics and also the initial state distribution. And then the next situation is that after we get this similarity in success rate, fine-tuning the source policy on a target task with similar dynamics to the source task will be very efficient. And as such, they propose a metric for retrieval, which is the zero-shot transfer success between the source policy and also the target task. And by doing this, they propose to first learn a function F that is able to predict the zero-shot transfer success for any pair of source path and also target path. So before we are able to learn the transfer success predictor, we need to be able to have a strong utilization for both the source policy and target task to be able to efficiently learn a function F. And in this paper, they propose to learn three main features, which is the geometry of the parts, the interaction dynamics, and also the expert action for solving the task. And yeah, so they propose to able to learn all of these embedded features and then to represent one task. And in the first step, they try to learn the geometry by feeding the CAD model and the geometry of the object by training an encoder to be able to reconstruct the geometry of the object as point clouds. And then the next step is to be able to learn the features for the dynamics and also the expert actions. However, this is very challenging because we assume that in the paper that we do not have any access to new demonstrations for the new assembly task. And to generate new assembly demonstrations is very intractable and very time consuming. So proposal they did was instead to do generate a disassembly trajectory in simulation, where for example, they have a start pose of the object already inside a socket here, and then to generate trajectories for the assembly from move the plug to another random pose. And after getting these disassembly trajectories, we are able to learn the dynamics and also the action features. And for the dynamics, we do a state prediction where we ask we train encoder to be able to predict the next state. And then for the actions, we train encoder to be able to predict the next actions that is predicted. So after training after getting all these three features, which is the geometry, the dynamics, and also the expert action, we concatenate them together to form the feature of the task. And then we do training for a simple NLP to be able to predict the transfer success of the task. So next is they do some experiments to be able to evaluate if this method of transfer success predictor is feasible or not. And first they do training where they learn the transfer success predictor with training data from a set of prior tasks. And then to evaluate the transfer success predictor, they do on a set of test tasks from to select a source policy from prior tasks. And they take 100 tasks from the previous framework automate and have 90 prior tasks as their scale library, and then 10 tasks are given as the test tasks. And when compared to other baseline retrieval strategies, such as, for example, only using geometry and other baselines, overall, we found that this method of retrieving source policies obtained around a 10% higher success rate on the test task. So next, now that we have the skill retrieval framework, next is how do we adapt these retrieve policies to new tasks. And in this step, their ultimate goal is to solve this new task as a reinforcement learning problem. So after being able to retrieve the source policy, they initialize a policy network with retrieve skill. And then they propose to fine-tune this policy on the target task again, using proximal policy optimization and also self-imitation learning. And they do some experimental setting in both a dense reward and also a sparse reward setting. And they show quantitatively that in both settings, both the sparse reward setting and also the dense reward setting, SRSA is able to outperform the automate baseline and achieve higher success rate with fewer training epochs. And here is an example of deploying SRSA on a real world task. So they first fine-tune their policy in simulation using some simulation, and then deploy the fine-tuned policy in the real world. And they showed that when comparing SRSA with the baseline, which is automate, they achieve an average success rate of 90%, which is significantly higher compared to automate, which only achieve around 54%. So next, once we have the skill retrieval and skill adaptation framework, the framework is tested on a continual learning setting, where we would like to learn various tasks in a sequential fashion. So what this means is that we start from a skill library of only 10 tasks, and using a continual learning setting, we expand this library incrementally. So for example, starting from a skill library of 10 tasks, we obtain 10 new policies for 10 new tasks, and because we use a data set of 100 tasks, we repeat this process for over 9 iterations. And in this continual learning setting, we also compare the overall sample efficiency between SRSA and automate, and they showed that in this setting that SRSA is able to be efficient even as they evolve the skill library and also the target tasks, and they only require fewer training stages compared to and to achieve higher success rate compared to automate. And to be able to evaluate the importance of each component, they tried to do several observation studies, mainly on 3 things. First, the effect of skill retrieval, and then next is the effect of the self-imitation learning method, and then next is the effect of using a generous policy instead of specialist policy. So for the skill retrieval, they compared SRSA, which uses 3 different task features, comparing to only using geometry-based skill retrieval, and they show here that SRSA improves the efficiency of adapting new skills over only using geometry-based skill retrieval. And then next, comparing the SRSA with self-imitation learning and without self-imitation learning, and they show that SRSA is able to outperform the variant without self-imitation learning in terms of learning stability, where not using self-imitation learning, the variant suffered more fluctuations and also higher standard deviation for the success rates. And lastly, they studied the effect of fine-tuning a generous policy instead of selecting a specialist policy, and they showed that when using a generous policy, SRSA provides a weaker immunization compared to using a specialist policy, and adapting new skills is also less efficient and requires more training stages. So overall, they showed that skill retrieval and self-imitation learning and also using a specialist policy is quite important to be able to transfer new skills in assembly setting. So as a conclusion and to summarize the overall results of the paper proposes a pipeline for retrieving retrieving skills and also adapting these policies to solve new assembly tasks. And they do this by combining skill retrieval with also policy fine-tuning and self-imitation learning. Several limitations was addressed in the paper. For example, they only tried simple tasks and did not consider tasks that needed rotational or helical motion assemblies, such as nut and bolt. And also they primarily focused on special single task policies, while maybe exploring new general policies might also be an interesting line of work. And next, because the target is for assembly deployment in assembly tasks, the real world success rate of 90% is still very short of the 99 plus success rate that is needed for industry level deployment. And they attribute this to the synchronal gap and the decrease in performance when transferring from simulation to the real robot. And for future extensions, several things can be done to extend the framework, such as how can we utilize existing policies for new tasks beyond just assembly tasks and also more general purpose manipulation. And then also to extend the framework for more complex tasks and not just insertion, but also tasks in other domains such as tool use and other complex manipulation. So that concludes my presentation for this paper, and thank you very much.
ジェレミーさん、ありがとうございました。何か質問ある方いらっしゃいますか？
Yeah, I have one question. So in page 12, I think the assumption here is that the dynamics. So I wonder if it actually holds that the assembly dynamics and this assembly dynamics is the same. Do you think it holds? Like if the assembly and then if the task is similar between the two tasks, then assembly and disassembly dynamics it should be similar.
Yeah, I think it's a case of also the task that they're considering. They only consider, for example, insertion where it's only kind of simple up and down movement. So if you consider more complex trajectories that need more maybe trajectories that are very complex, then using this kind of disassembly trajectory is probably does not capture the same dynamics. So I think in their simplified approach, it's a reasonable assumption that they use this kind of method because maybe collecting new demonstrations is not feasible. But I think to be able to extend it to a more complex manipulation, I don't think this kind of approach holds to actually the same dynamics.
Oh, this is actually just for training the predictor to predict the transfer success rate. So maybe that's enough.
Yeah.
他に何か質問ある方いらっしゃいますか？ありがとうございました。